Good morning, here we are. It's the psci 168 video lecture. psci 168 video lecture 1. My name is Carl Rundy. I've already sent you a syllabus, and what we'll do today is I'll go over the syllabus and hopefully answer a lot of questions that you have. And then we'll launch into the new material. So let's get started. So what is this class? Energy and the environment. Energy and the environment. Like I said, my name is Carl Rundy, and we'll mostly be communicating by email. So I'll say a lot about that right now. This is my email address. krunde@csufresno.edu. So pretty much all of your work is going to be addressed to this email, not Canvas. And for the moment, we don't have any Zoom projects. What we're doing is everything on my YouTube channel. Okay, so it's all my YouTube channel and this email address here. And I'll be getting a lot of emails. If I don't answer one, just send me another one, okay? I'm not ignoring anyone. There's a lot of emails coming in. This worked very well last semester, so it's gonna work well this semester too. Okay, so energy and the environment, spring 2021. I'm just reading off my syllabus here. It's really only the first page that we have to talk about. The second page is a bunch of formal stuff. Okay, so what do we have here? Office hours are by email. So I'm already down on several lines down there. Next, there are no required books for this course. Instead, your lecture notes are going to turn into a book, and I'm placing a really great emphasis on the lecture notes, as I'll explain as we're going through this. So there's no required book, and really there is no book that exists that would do what we're doing this semester. Class Monday, Wednesday, Friday, 3 video lectures per week. You can actually watch them anytime. What I want is every Friday, your handwritten lecture notes emailed to me in the form of a picture that you took. You can actually spread them out on a table or one by one, but I need an email sent to me every week, Friday, no later than 6:00 p.m. of your lecture notes and any little projects and stuff that I'll assign as well. So yeah, let's write that down here. This is the email address that you send them to. What I want you to always do is open a new message, because when we reply to a mass message, sometimes things get lost. But you always open a new message. So homework, etc. every Friday, new message. And then the subject of the message is just always going to be your name, our class, psci 168, and then homework. We don't need commas there. But this is the subject, and that way it'll definitely get to me and I'll check you off. Okay. So, and these lectures, 1 through however many we do, 3 a week for the rest of the semester, will be on the YouTube channel and the playlist, psci 168 playlist, which is where you're going to find them. Okay, so moving on through here, we got the class Monday, Wednesday, Friday. You can watch the lectures anytime you want. When we have our exam, we will use the class time to do the exam. And I have written here examination, midterm, and then a final exam. So the dates are given and the times. And the weighting for the grade Homework and notes 30%, midterm 25%, final exam 45%. And then I have the letter grade scale. Any curving will be done at the very end of the semester, okay? So don't worry about that right now. I've taught this and all manner of students have been very successful. It's going to look really technical for some of you because we're just going to launch into math and stuff, but I'm going to build everything up step by step. So be confident and optimistic. And the main thing for starters is these lecture notes that you're taking. So I'm going to read this again. Pictures of your handwritten lecture notes, homework problems, printouts from online sources, and home projects must be sent to me by email every Friday evening. So our book is going to be the lecture notes. So when we take notes, what I want you to do is leave a lot of space in your notes. Probably best to use loose leaf paper and assemble a binder, because we're going to have the notes. I'm going to ask you to look things up online so you print out some nice pictures and insert them in there. At the end of the semester, maybe I'll block this off and write that out. At the end of the semester, you're going to number all of the pages in your notes, and pictures and everything. You can number them all. You can make a table of contents, maybe a glossary and an index as well. That'll be the last assignment, and then you'll really have a nice resource. I'm going to have this table space, as I have right here, to show you physics demonstrations, and some of these you'll be able to repeat at home and take pictures of those and put those in your notes as well. So we had really nice results last semester, some of those notebooks. In fact, I have to look up some students and maybe get a copy for my own records. Okay, so it can be really good, and all manner of students have taken the class and succeeded. So even if you're not that mathematical, just work along and have some confidence. Good. So next, I'm going to put a little outline of what we're going to do. I'll put a little outline. It doesn't all have to come up here at once anyway. Again, and I'll repeat this at the end of the hour, as long as you email to this address and your name, and homework here, and everything will arrive, and we'll just build up from there. Okay, good. The next thing I'm going to do is an outline of the material. So I'll leave the title up here, Energy and the Environment, because energy is a concept from physics, and I'm going to give you about 2 semesters worth of energy physics. But let me explain how I'm going to build it up. We're going to build the whole subject up from scratch. From my first topic is people chasing, wild game out in the desert, and how they use reasoning to improve their chances of bagging game. And literally we're going to start there and then work our way up through geometry. So let me give a little list here of our topics. It will actually take a while before we get to the concept of energy, because like I said, we're building everything up systematically. So we're going to begin with reasoning and the hunt. And this is going to lead us directly to the need for geometry and arithmetic. So if you ever wanted to know why you need geometry and arithmetic, this is going to be the place. Geometry and arithmetic. So we're going to do some study of mathematics, namely the mathematics that we need. Okay. Of course, the assumption is you've seen it before, but we're going to put it all into context. One example of this is going to be the number of days in the year. what is a year? Okay. What is a year? And we're going to talk about sundials as well. So I've got some examples from that, and combining some of these topics, astronomy. You can't have one without the other. Then, finally, we get to forces and, or I'll just write force singular, force and structures. I have an idea that we want to talk about aqueducts this semester, a good topic, and we'll need to know about structures in order to deal with that. So force and structures, and only then can we get to what energy even is. Okay. But that will actually just be a rudimentary description of what energy is. We still have to talk about motion. I'm going to combine some topics here. Motion, and as a very nice, here, let's go ahead and say motion, comma, free fall, and as a very nice application, satellite orbits. Satellites that orbit our Earth, for instance. Satellites, and only with these concepts can we talk about Newton's laws, and only after Newton's laws can we return to energy. And this time I'm going to write energy conservation. And at this point, we're right in the heart of our semester, and we can talk about hydropower as a really good example. And this one is very central to the entire semester. And so this puts us right in the middle of the semester. I'm just going to indicate what follows. We then have a large section on thermal physics in order to talk about heat engines and power generation. We'll cover solar energy, all these things from the standpoint of the fundamental, the basic physics of it all. So heat engines, followed by, I'm just going to put etc. here because I can't list everything, but we will have a major section on electricity and magnetism. So let's go ahead and write that down. Electricity, magnetism, and transmission of power. Okay. Transmission. So that is quite a bit, and we're not faking it here. This is going to be the real physics of all of these topics, and you'll be amazed. Okay. We hope to have an overview of the whole topics, energy on the personal scale, municipal, global, okay, energy amounts. So this should be good. And I'm supplying all of the logic, and you guys are putting together a book with the notes. So once again, leave a lot of space in your notes, and I'm going to have you download pictures and insert them in, so you'll have a colorful book. And like I said, at the end of the semester, you'll take all your pages and number them, construct a table of contents, maybe a glossary, definitely an index, because at the end of the semester, when you construct your table of contents and your index, you're going to get a review and an overview of the entire subject. Okay, so this is something I'm looking forward to because we had a pretty successful semester last semester, and we can have an even better one this semester. So that is the basic overview, and I'll say one thing about this. We're trying to develop everything from scratch, and I'm going to start with a couple of topics here today, but everything that comes before is needed for everything that comes afterwards, and that's why I say I'm supplying the logic of this. Everything's going to be developed logically, and when we get to energy, for instance, we don't know enough yet to really understand energy. We have to go back and study motion and free fall. But the study of motion is interesting in its own right. Satellites and how fast they move in order to be in orbit, say around our Earth, interesting in its own right. And I usually make as a problem on an exam the derivation of the satellite orbital speed. And that's not something you can do now, that's something you'll understand then, but it's going to require all kinds of stuff from earlier. Okay, so that is as much of an outline as I'm going to give now, because you actually have to go through with the whole program to actually see all the logic in it. Let's see how we're doing here for time. Okay, excellent. So we're going to move on into the actual subject matter. I'll just give this one more look. Any questions that you have, just send me an email. And be patient, and if I don't answer the email, just send me another one. Okay, I'm getting a lot of emails. I'm not ignoring anybody. So just send me an email if you have a question, and I hope to get back to you as soon as possible. Good. So let's get started. What we're going to talk about is some basic reasoning that's used in the hunt. Now, I'm not a hunter, so I read about this, but I'll give you some of my sources, some things you can look up as well. So we're starting with the beginning topic here. And I read about this in a book by Richard Lee, who's an anthropologist. So I'll just put here for your notes. Richard Lee, he was pretty well known. He worked with people in the Kalahari Desert down in South Africa. But the argument was about tracking game. So I'll write that down. I'm going to draw a little picture. So the hunters are tracking game, and well, my pictures aren't that great, but I'm sure the trees in the Kalahari look a little different than that. Fine. They're tracking game, and the tracks go around here, and there's a collection of them here. So the interpretation is that the animals, they're going in this direction. They came here, and then they went on. So I'll put a little arrow here. There's my tree, there are the tracks. And the question is, what happened there and when did it happen? So here's the quote. The principle in the desert is that the traveling herd hates the sun. Okay, this is the quote that I remember. Traveling herd hates the sun. Well, that just means it's hot there, and when they run into some shade, they take advantage of the shade, and so they rest in the shade. Well, if they rest in the shade, when you came here later, there wasn't necessarily some shade there. But when they came there, there was some shade, and that means that the sun was coming from this side of the sky, casting a shadow, and there was shade there, okay? So they hate the sun, and know they like the shade because it's on the desert. What that means is our hunters here can estimate how long it's been since the herd was there, because now maybe the sun is somewhere else in the sky, right? There's no longer a shadow there, but the herd was there when there was a shadow. Okay. So that's an example of logic and reasoning. And it's another example, it's an example of a sundial. In other words, implicitly or explicitly, we actually have the sun moving across the sky, and we have a timepiece. In other words, this tree represents and is actually a sundial of sorts. Okay, so let's hold fast to this. So first of all, we have, logic and reasoning, and you see that's pretty universal. You want to get your next meal, you got to use some reasoning. And there's a principle here, so they're reasoning off of a principle. And the second thing we have is we actually have an example of a sundial. I can put this in quotes and scare quotes for a sundial, because it's just a tree, and it's probably not a straight tree either, okay? It's just a tree that casts shade. So traveling herd hates the sun, which means they congregate in the shade. You guys can make a nicer picture than I have here. Leave plenty of room in your notes. But we've got this example of a sundial, and so I brought a ruler to class, because what we want to do is get the abstract version of this tree, and that would be a vertical stick that casts a well-defined shadow. Okay, so if I have a vertical stick casting a well-defined shadow, say the sun's back here, it's casting it on the table. If I have a vertical stick casting a well-defined shadow, then I actually have to stand this thing up, right? Good, there you have it. Then we have an example of geometry. We now have geometry relations between a vertical stick, angles, a flat tabletop. Okay, so example of a sundial. And right away, my third point, if we just generalize this and abstract from it, we need geometry. If we're going to do something with this idea, but with more precision. Okay. So that's how we get from just basic reasoning, chasing our dinner, to talking about logic, sundials, and the need for geometry. And I also had there on my list arithmetic, so I'm going to start a second example as well. So next, how many days in a year? And we're going to tie it to these geometrical things, and then we'll have both of our topics on the board. Because how many days in a year? You guys know 365. Okay, but that's a pretty big number. If you got 5 and 5 is 10. You get your toes as well. That's 20. So 365 is actually a pretty big number. And to deal with numbers like that, you need arithmetic. And as we're going to see, you actually need some geometry to discover the answer to this question. So that's what I want to set up next, and I think that's what we'll continue to discuss today. I'll put together a little homework for you. So far, we're going to want to talk about geometry and arithmetic in the context of how many days in a year and the use of a sundial. Okay, good. I'm going to go ahead and erase this. So let's stand this ruler up once again. Could we use this vertical ruler, say we're outside, to measure the number of days in a year? Okay, we want to measure the number of days in a year using this ruler. Sounds kind of like a joke because we're measuring a number and this ruler is length. But the shadows is what we're after for the moment. So let's go ahead and talk about a vertical stick casts a shadow on the ground. So now we have to imagine we have a clear sky, we have sun, we have a flat piece of ground, and we have a vertical stick represented by that ruler. Shadow. Okay, so the vertical stick casts a shadow. Vertical. And for the purposes of that, I'm going to put my ruler here. Okay, I happen to have this kind of square cross section of a ruler. And we'll let the sunlight come from here, and the shadow that it's going to cast on the ground, I'll go ahead and, I've got colors here, so I'll use blue. Okay. There's the shadow that it casts on the ground. Okay. Now, this is pretty good. We have vertical stick. We can imagine north facing class, south in that direction. So what time is it right now? What time is it here on my picture? Okay. Well, taking a little profile into account, this could be noon. We could imagine this shadow is being cast pretty much directly toward us, and the sun is behind the ruler. Whereas in the morning, we will have a very long shadow being cast over here, and in the evening, we'll have a very long shadow being cast over there. So this shadow is actually going to be cast on the ground where early morning here, noon, and then evening over there. So not only does a vertical stick cast a shadow, the early morning and late evening shadows are very long. The shadow at noon is short. In fact, the shadow at noon is the shortest shadow that's being cast. So I've got vertical stick cast a shadow, and shortest shadow at noon, and here in the northern hemisphere, that shortest shadow is actually pointing directed true north. So shortest shadow at noon, points to true north. That's one you may want to ponder a bit, why that's the case. If you have a globe and you imagine where the sun is, you can actually figure that out. So the shortest shadow points to true north, and it's at noon. Okay. So the next thing in this progression of ideas is that the length of this noon shadow changes during the course of the year. So here, let's just imagine for a moment that the sun is very close to directly overhead, and the shadow is short at noon. Won't be that short. Say it's there. Tip of the shadow is right there. Not sure what you guys can see, but it's all right. Okay. So there's our sundial. Sun's coming from behind. Tip of that pen is the tip of the shadow. At noon, what you'll notice is in the winter, the sun is closer to the horizon, and the shadow that points north is longer. Okay. In the summer, it's shorter. So if you were to have a very well-constructed our sundial is just a vertical stick here and a nice flat piece of ground, and you measured out the shortest shadow, put a little mark there every day, then in the summer, that distance from the stick to the tip of the shadow would be shorter, and in the winter it would be longer. Okay. So you'll notice I'm already talking about relations that, if we want to discuss them accurately, require geometry. Okay. Shortest shadow points to true north. So my third point here is, and we're going to call this the noon shadow. So the length of the noon shadow, we're just going to call it that. It's that shortest one at noon, changes over the course of a year. So if you were to do these observations for a long time, the shadow length would change and it would come back again, it would change and come back again. So length of the noon shadow changes over the course of a year. And let's go ahead and graph this. Nice to do some graphs. And what we're going to do is title this graph. We're going to title it length of shadow at noon, noon shadow. And I can call that L. And then down here on this axis, we're just going to call this the number of days. We're going to call this the number of days. And so we're making our measurement every day. Some days are cloudy, can't make the measurement, but when it's clear we can. And what we're going to find is, so right now we have winter, so there will be the longest. We're going to find this pattern like this. And on and on. So what am I drawing there? Got the longer shadows and they get shorter. Whoa, that must be summer, right? Longer again, shorter again, summer again, and on and on. You could even say the length of the shadows and the length of the days is the opposite of each other. So we're talking about the shadow. And what do we have here? We kind of connect our data, got a curve. And now, what is 1 year? 1 year would be, say, from there to there. Could either be peak to peak or trough to trough. And then we had a bunch of days here, and we added them all up. We get 365 days. So you'll notice that that question of the number of days in a year actually depends on astronomy, because this shadow was cast by the sun. Okay. So we've got astronomy, we've got geometry. The fact that it's 365 days means we also have arithmetic. And what should we title this here? Yeah. This was called How to Measure the Number of Days in a Year with a Ruler. Let's go ahead and write that down as well. Number of days in 1 year using a ruler. So it wasn't a joke after all. And there's actually another topic here that I want to get to, and that is accuracy. Because the fact of the matter is, it's not going to be easy to really determine that this is 365 and not 370. Because you'll notice when I'm going from the trough to the trough in my graph, it's hard to tell when it really is the shortest shadow, because it changes very little for a number of days. Maybe for an entire week, everything is almost the same. So accuracy would come in with better instruments. And practically speaking, we wouldn't use the sun, we would use stars. You know, we would do a related type of thing using stars at night, and then they'd be pinpoint, we'd have pinpoint accuracy. But for the purposes of our, our storyline here, we can do it with the shadows. And the question of accuracy, I also want to get up here on the board. Question of accuracy is going to require us to have accuracy in everything. The stick has to be straight. It can't shift over the course of the year. The ground has to be level. Okay. The lengths have to be measured with great precision. Maybe we have to measure angles, that type of thing. So I want to add to this here. Well, since I'm just using this one board, I'll have to erase something. Okay, but you guys have this. So the next thing is the question of accuracy. So point 4 in my list here is going to be accuracy. So point 4. Accuracy. I'll put a question mark here for the accuracy. Well, this time let's draw our ruler kind of in the abstract. So how about we'll just draw, and we'll draw a right triangle, and then we have the length of the ruler, the length of the shadow, we've got a hypotenuse. Okay. We can analyze the situation using geometrical concepts. So I'll just call this L for the length of, well actually I used L for the shadow. Once more, see I get a better picture here. Good, about the same. Okay, this was the length of the shadow, so that's L, and I'm just going to call this A here for the length of our ruler. We have a right triangle. We have a couple of angles available if we want to use, I'll call these alpha and beta. If we want to use geometrical knowledge to help us measure these things and relate one quantity to the other. So for the accuracy, we need geometry, because we just need precise ideas as well as precise instruments. So we definitely need geometry, and we're going to do some study of geometry the next couple of days with some interesting applications beyond this. So we need geometry. And what do we need the arithmetic for? Well, I said we have these numbers. The graph I just erased, 365 is pretty big. You do that for 10 years, you need 3,000. So we have to be able to deal with large numbers as well. So geometry and arithmetic both, and we'll do a bit of a review of some interesting aspects of both. Oh yeah, here is a homework. You'll notice I have some Greek letters here, alpha and beta. So what I want you guys to do is download and print out a Greek alphabet. So print out, because we'll be using Greek letters here and there, and then you'll have them, you can refer to them, practice writing them. Print out the Greek alphabet. Print it out, show me that you printed it out. It's part of your notes now, it'll be inserted somewhere into your notes. So print out the Greek alphabet. Let's see how we're doing time-wise. Okay, we have a couple more minutes, but we're doing pretty well here. So let's see, print out the Greek alphabet. And since we're going to study geometry, I'm going to begin with a little study of arithmetic, namely scientific notation. So let me put here next what we're going to do this time and especially next time. Arithmetic and scientific notation. And geometry. So we're going to study these things. For example, I've got a right triangle. We're going to prove the Pythagorean theorem. We'll get some applications of similar triangles and stuff like that. So geometry, arithmetic and scientific notation, and geometry. I think I'm going to leave it there for now, okay? Because this was a good place to stop. So, as we said, so I'll repeat what we said at the beginning. You want to construct these really good notes because they're going to turn into a book. And we started with this reasoning in the hunt, and we went to the sundial. We saw that we need accuracy, we need geometry. I'm going to show some more why we need arithmetic, scientific notation. So that's the preliminary. You'll be turning this in as well as Wednesday and Friday notes into me once a week on Friday. And print out the Greek alphabet. You can find many Greek alphabets online. Print out a nice page of the Greek alphabet, lower and uppercase, and include those in your notes. So that's what we'll do. Next time, we'll dive right into some geometry and scientific notation. Big numbers, small numbers. Okay, until then, anything else? No, that's good. So, see you guys next time.